All right, so we are recording also. We go to session number 3. Let me close some of this screen. Okay, can I minimize this? All right. Let me, a couple of questions from last session, session 2, want to answer before we go to session 3 for assignment number 3. All right. Okay. We had this question for assignment number 3. Few of them, you guys had some of them, you had problems. I want to explain them. Questions number 1 through 3 talks about find out, determine which collections are not well defined and therefore not set. Okay. The first question is the collection of all the part-time and full-time students currently enrolled at Southern California Seminary. Well, the question we have to ask is this a well-defined set? They're talking about all the part-time and full-time students currently enrolled at Southern California Seminary, which this is very well defined. This is a set. The second question talks about the collection of all the elderly full-time students currently enrolled at Southern California Seminary. This is not a well-defined collection, therefore is not a set, because you have to define what do you mean by elderly, what age. You have to put a marker, an age marker, to make this a well-defined set. Number 3, the collection of even natural numbers greater than 100. Okay, again, this is a well-defined set because they're making a specific even natural number greater than 100. All right, I hope this is clear. Let's go to questions. Let's see. Number 9 and 10. Some of you had problems, some not. But let's look at them. Questions 9 and 10. Let me make sure that you guys can see the board behind me, because I want to go and write some things on the board. It gives you a universal set, U, A, B, C, D, E. Then it gives you 2 subsets, A and B. Let's talk. A is B and C. Let's write these on the board. Show that this is clearly seen. Okay, so we have this universal set A, B, C, D, and E. Yeah, you can see that. Okay. And then we have set A and set B. Set A is B and C. And set B is set B is BCE. Okay, so these are given. Always make sure you know what is given. Then the question number 9 is asking you union of A and B, parenthesis prime. Union of A and B, parenthesis prime. And again, let me make sure. Yeah. Well, the union of A and B, what's in both A and B would be B, C, and E. Okay? That's the union. But then we want it prime. So we are looking for what that means what's not in this set. So you go to your universal set, you don't want B, C, and E. You don't want B, C, and E. So it's only A and D. So the answer, the union of A, set A and set B prime would be a set of A and D. Okay? Now, the next question, watch this for a moment. The other question is asking question number 10, the intersection of A prime and B parenthesis prime. So this is for that. Now, go to the other one. So you want to find intersection of A A prime intersection with B, then the whole thing prime. All right? Make sure that I got it right. All right, so what would be set A prime? Meaning A prime means whatever it's in set A, not in set A. Set A has B and C. So we don't want B and C, so you have A, B, C, E, and E. We don't want anything in, we don't want A and B and C because we want A prime, so we don't want B, we don't want C, so it's A, D, E. A prime is A, D, and E. All right? Set B is B, C, and E. It is asking for the intersection. That sign means intersection. So intersection of A prime and set B. What is common in both of them? A is not, B is not, C is not, E is there. So it's only an E. All right? So this is intersection. This would be this part. E prime. E. Then not E. We are asking anything not that. So it would be, are you following me? Yeah. Let me do it again. This is what we are trying to find out. Not A intersection with B. We saw not A would be A, D, and E. Not A would be A, D, and E. B is B, C, and E. Intersection, meaning what is common between them. it's only E. So intersection of these two is only E. What we want, E naught or E prime from the universal set. So you get A, B, C, D. That's it. That's the answer. A, B, C, and E. Let me just see. So I go over this one more time. This is our universal set. This is set A. This is set B, which has B, C, and E. Okay? We are looking for a set of this. We want A prime, meaning not A, meaning what is not in set A. What is not? Set A has B and C. What is not in set A would be A, D, and E. What is set B? Set B is B, C, and E. Intersection means what's common between both of them. The only thing that's common in both of them is E. So intersection of A prime and set B would be E. But then we have this sign up here. Prime of that, not of that. So we go back to the universal set. We say we don't want E, so that would be our answer. A, B, C, and D. All right? I hope this is clear. All right. That's about that. Let's go. Okay. Other questions are, I think, clear. The only thing about the last one, number 14, some of you have made mistake, the Maya numeration system. Listen, it's that line means 5, that oval shape means 0. The line above that, okay, is 5, 0, but the position actually 5 sets of 20. So it would be, the answer would be 100. Okay. I think everything else is clear. We talked about everything else. All right. So that's about assignment 3 from lesson number 2. Then let's go, a couple of things. Regarding your PowerPoint presentation, we discussed that last night with the in-class student. Maybe it's better to submit all of your PowerPoint presentation for everybody at the end of the course. So session number 7, I expect everybody to send your PowerPoint presentation. Please follow the syllabus. Please pay attention to what I put on Populi for each session, each week assignment that you have, and please submit them on time. Let's go to now to session number 3, lesson number 3, and go over our lesson. Oh, about that 60 little known facts. You can use internet, you can do the Google, you can use your textbook notes, you can even talk to each other, and I give you a hint. Lots of the answer for those 60 little known facts, you can find them in the videos that I put that in lesson number 2. If you go to lesson number 2, there were a number of numerations that you can find. Let me show you if I can. Okay. Yeah, basically, if you go back to all the videos that I uploaded from Populi, let me, if just take me a minute to get there. Signing to Populi. One moment. You know, if you go under session 2, ancient numeration system, I have uploaded all kind of videos for Greek numeration, Egyptian numeration, Romans, Babylonian, Chinese, Mayan, all kind of stuff. And you can find those information, and they will help you to answer those 60 little known facts about math. But please remember that 60 little known facts, actually, I designed that to make it as a something substitute for your term paper. We don't have a term paper in this course, but that will act like that. That will kind of function like that. And remember, for each point, the maximum value would be 0.5, half a point. So don't worry about it too much. Do your best, but if you miss some, each question only has a value of 0.5 overall. So do your best. I think if you watch those videos, all the videos, not just the one on session 2, but all the videos, if you read your chapters, and which you're supposed to do, and notes, and you can talk to each other, you can even Google some of the questions, I think you will do good. All right? So then let's go back to session 3 and to our PowerPoint. Lesson for session 3. In this session, we talked about number theory and real number system. We use number as a representation for facts in the universe, facts in the real life. Number theory is a study of numbers and their properties. And now I'm just following from the PowerPoint. So please open your PowerPoint and follow with me. Some of the things that I need to write on the board, you can use this video. The numbers we use to count are called the counting numbers or natural numbers, because we usually counting with the number 1. The set of natural number begins with 1 and is denoted by capital N. Then you have those signs, and 1, 2, 3, 4, 5 to infinity. Any natural number can be expressed as a product of 2 or more natural numbers. 2 times 3, 6, another natural number. 4 times 5, 20, another natural number. So these are called the factors. 2 times 4, 8, 16 is 4 times 4, and so on. The natural numbers 1, 2, 3, and 6, 9, and 18, all are factors of 18. That when we say that, we mean that each of these numbers divides 18 without any remainder. We're talking about divisibility. If A and B are natural numbers, we say that A is a divisor of B, or A is divisible by B, or A divides B, and the symbol that we use is A, that little straight line, perpendicular line, then B. If the quotient provided, the quotient of B divided by A is 0, has a remainder of 0. If A divides B, then B is divisible by A. Basically, that's what we are using. 4 divides 12, symbolized by 4, that little straight line, 12, because the quotient of 12 divided by 4, the quotient is 3, remainder is 0. Every factor of a natural number is also a divisor of the natural number. Please don't confuse symbols A straight line B with A the slanted B or A divided by B. A straight line B means A divides B, but A slanted B means A divided by B. We talked about prime and composite numbers. Every natural number greater than 1 can be classified as either a prime number or a composite number. Prime number is a number that can be divided only by 1 and itself with no remainder. A composite number is a natural number that is divisible by a number other than itself and 1. Number 1 is called, it's neither prime nor composite, it's called a unit. For example, on the PowerPoint you have that table, numbers going from 2 to 100, because we said 1 is a unit. We want to find the prime numbers less than 100. So what do? We start with 2, and then you just find all the multiples of 2 and cross them out. 4, 6, 800. Do the same for 3. Then you go to 5. Then you go to 7. In this way, you are eliminating all the composite number, because these are numbers. If you go to other slide, for example, 4 is crossed because 4 can be divided by itself, can be divided by 1, and can be divided by 2. That's why we did the multiplication. We multiply 2 by 2 by 3 by 4, and all the result, we cross them out. Those are not prime because they can be divided by either by themselves and 1. You go to 3, same thing with 3. 4 is crossed, so you go to 5, all the way to 100. And the one that are circled, these are the prime numbers between 1 and 100. Some of the fundamentals, theorem of arithmetic. Every composite number can be expressed as a unique product of prime numbers. You get 2 prime number, multiply them together, and we use a factor tree, if you remember from high school, factor tree to find prime factorization of a composite number. We have a composite number. We want to find what are the it is composed of a product of set of prime number. We want to find them. So we start with that prime composite number, and then we find 2 product that gives that number, and we keep going all the way down. In other words, if you go to the slide that shows 210, it's a composite number. We want to find all its prime, so we go through this composite tree. 210 can be the product of 2 times 105. 2 is prime, so we leave that alone. 105 is a product of the 3 times 35. 3 is prime, we leave that alone. 35 is a product of 5 times 7. And then we stop, because 5 and 7, they are both prime. So the composite number 220 is a product of the prime numbers 2 times 3 times 5 times 7. We go another way. 210 can be the product of 14 times 15. 14 can be the product, neither of 14 and 15 are prime. 14 is a product of the 2 times 7. They are both prime. We stop right there. 15 is a product of 3 times 5. They are both prime. We stop, and again the same result. 210 is a product of 2 times 3 times 5 times 7. Same thing that we find in the other way. Or you can do the prime factorization by division. I prefer prime tree, but you can use also division. You start number 34,200. You divide it by 2 because it's an even number. It can be divided by 2. We find How do I know it's even? Because it ends with 0. It ends, if it ends with a 0 or an even number, it can be divided by 2. Then I find the other one. When I divided by 2, I got 17,100. Again, I divided by 2. The next number, I divided by 2. When the fourth number ends with a odd number, it cannot be divided by 2. I go by 3, and then I get another number, 1,425, divided by 3, and keeps going all the way till I reach 19. Then I stop, because 19 is a prime number. So the number 34,200 is a product of 2 times 2 times 2 times 3 times 3 times 5 times 5 times 19. Now, we have a couple of important terminologies in arithmetic. One is greatest common divisor, GCD. The GCD of a set of natural number is the largest natural number that divides without a remainder every number in that set. For example, what's the GCD of 12 and 18? Okay, let's divisor of 12, meaning a set of number that 12 can be divided by that number without any remainder, are 1, 2, 3, 4, 6, and 12. Okay. Divisor of 18 is 1, 2, 3, 6, 9, and 18. As you can see, these are in your PowerPoint. Then we want to find the GCD, the greatest common divisor. First, we find what are the common divisor between these two sets. They are 1, 2, 3, 6. Okay, they are in bold. The greatest, the largest value is 6, so GCD of for these two sets is 6. Now, if you want to find the GCD of 2 or more numbers, again, we find the prime, we use the prime factorization for each number. Then we list each prime factor with the smallest exponent that appear in each prime factorization. Then we find the product of the factors find in step 2. For example, let's go to some of the examples, and here I'm going to use the blackboard. Page 232. Let me, a moment. Glasses on. We go to page 232. And we look at the examples here. Page 232. Example number 3. We want to find the greatest common divisor of 216 and 234. So, as you can see in your textbook, 216, we use the three factoring, and 216 can be the product of 2 times 108. Then 108 is product of 254. 54 2 times 27, 27 3 times 9, 9 is 3 times 3. We stop because they are both prime number. We are using 3 factor. Okay. Now look at if you look at this factor tree, we have 2 times 2 times 2 times 2 and 3 times 3 times 3. So we write it. Let me make sure that you are seeing me. So we have this number, which is 216, and we use the tree factor. We find it can be, or it can be, it's a product of the 2 times 2 times 2 times 3 times 3 times 3, which this can be written 2 to power of 3 exponent 3 times, because 1, 2, 3 times 3 to power of 1, 2, 3, power of 3. You do the same tree factor for number 234. Number 234, this, the next number. And again, we use the tree factor. We find it can be, it's a product of 2 times 3 times 3 times 13. Or it can be 2 times 2 times 3 to power of 2, there are 2, 3, times 13. Okay, so then we select each prime factor with the smallest exponent that is common to both of them. What do you see common in both of them? You see 2 is common between them, 3 is common between them. Well, actually, well, 2 and 3, actually, that's right. 2, well, what I meant was going up here. $234, it's equal to 2 times 3 to power of 2 times 13. Okay, there are 2, 3 here. What's common among them? 2 and 3. So we find the common factors, and we use the one with the smallest exponent. So it's 2 to power of 1 and 3 to power of 2. So here we get the GCD. The GCD, it would be a factor of the exponent associated with 3 is the factorization are 2 and 3, so we select 2. Therefore, another factor for the greatest common divisor is 3 to power of 2. So we find one factor for the GCD is 2 to power of 1, this one, and the other one is 3 to power of 2. These are the smallest number that can be used for division of these two numbers. All right. So you find you use a tree factor, and then you write those prime numbers in an exponential form. Then you select what's common between them. You select each prime factor with the smallest exponent that is common to both. Would be, when we look at them, it would be 2 and 3. The exponent would be the smallest one. The exponent associated with 2 in this factorization is 1 and 3, so we select 1. So one factor for the greatest common divisor is 2 to power of 1, or 2. The exponent associated with 3 is, there are 2 and 3, we select 2. Therefore, another factor is 3 to power of 2. What it means is these are the smallest, these are the greatest common divisor that is common between both these two numbers. Okay, let's continue with our PowerPoint. The greatest common divisor of a set of natural number is the largest natural number that divides every number in that set. That's how we find for 12 and 18, which was number 6. And when we have 2 or more numbers, we use the prime factorization, the 3 factor. We find the prime factor, we choose what's common between them, then with the smallest exponent. Then the product of the factors found in step 2. In other words, the answer would be 2 to power of 1 times 3 to power of 2, actually. These two, the product of them is the greatest common divisor. Okay. The least common multiple. The least common multiple. Okay, 1 moment. The least common multiple, or LCM, of a set of natural number is the smallest natural number that is divisible without a remainder by each element of the set. So we want to find the least common multiples of 12 and 18. Multiples of 12 are 12, 24, 38, and so on. Multiples of 18 is 18, 36, 18 times 3, 18 times 4, 72, 90, all that. The common multiples of 12 and 18, some of them, I wrote them in bolds, are 18, 36, 72, 108, and 144. The least common would be, the least common is 36, the smallest one. Is the smallest number that is divisible by both 12 and 18. 36 by 12 is 3, 18 times 36 divided by 18 is 2, and no remainder. Now, least common, to find the least common multiple for 2 or more set, again, we use the 3 factor. We find the prime numbers. We use prime factorization. We list each prime factor with the greatest exponent that appears. On the other one, we use the smallest. Now we use the greatest exponent, and we multiply the product of the 2 in from step 2. Let's, for example, on page 234 and 235 of our textbook, if you look at example 5, we want to find the least common multiples between 144 and 300. So we use the prime factorization. I'm not going to repeat that, and the textbook didn't repeat it. Then you find the prime numbers, you write them in an exponential form. 144 is 2 to power of 4 times 3 to power of 2. 300 is 2 to power of 2 times 3 times 5 to power of 2. We select every prime factors that occurs that is common between them, and we choose the greatest exponent. So we look at these two, we find there are 2 and 3. So the greatest exponent for 2 is 4, for 3 is 2. So we have selected, well, the 5 is not there. The least common multiple. So the greatest exponent appears 2 is 4. We select 2 to power the exponent that appears 3 is 2, and we select 2. The only exponent that occurs on 5 is 2, so we select 5 to power of 2. Thus, we selected 2 to power of 4, 3 to power of 2, and 5 to power of 2. Okay? Then, if we multiply these, we get the same number. The least common multiples of 100 and 300 is 36,000. The smallest natural number divisible by both 144 and 300 is 3600. So you see, we use a 3 factorization. We find the prime numbers. We wrote them in exponential form. Then we wrote what we have with the greatest exponent, 2 to power of 4 times 3 to power of 2 and 5 to power of 2. We multiply them. The answer we get, 3600, is the smallest natural number that can be divided by both 144 and 300. On the greatest common divisor, we find the prime factors, and then we write them in an exponential form with the least exponent, 2 to the power of 1 and 3 to the power of 2. We multiply them together, we get number 18. So the greatest common divisor, the greatest number that can divide both 216 and 234 is 18, which leaves no remainder. One thing that you see, two differences between finding a greatest common divisor and finding a least common multiple is, for the greatest common divisor, when we do the prime factorization and we write them in a prime factor, we choose the the number with the least exponent. For the LCM, least common multiple, we choose the number with the greatest exponent. In a GCD, we only write the prime numbers that are common between both sets, which was only 2 and 3. We didn't choose 13. But with LCM, we choose all the prime numbers that we have with the greatest exponent. 5 was not a common, but we chose that again. We put that in a product in a step 3, and we multiply it with the greatest exponent. We get the number 3600. All right. Now we come to integers. Basically, integers are, you have a number line. You can, all the numbers that are whole, 1, 2, 3, 4, 5. These are positive integers. -1, -2, -3, -4. Negative integers. 0 is the origin. We have both negative and positive integers. And when we have a natural number, 0 and negative of the natural number, with the positive natural integers, we have the set of integers. -4 and +4 are opposite of one another. Integer, basically set of natural number with 0 as the origin, and the negative of the natural number is called the set of integer. When we have both the positive natural numbers and negative natural numbers together with 0 as the origin, we have the set of integers. The number line is just to help us to visualize that, as you can see in your PowerPoint. Now, let's look at that PowerPoint, which I've written using the symbols less than or greater. For example, you have -4. Let me, for this one, go to the screen. We have, let me write these things down. Okay. Here we have -4. -4 and 3. We have -1 and -5, and -5 and -2, and 0 and -3. Okay, let me make sure that you can see this. Yeah. Okay, we want to put less than or greater. Which one? Between -4 and -3. Which one is greater? 3 is greater. This is -4. If you can look at that number line, if this is 0, this would be 1, 2, 3, 4. This would be over there. 3 is 1, 2, 3. It's over here. So 3 is greater than -4. Between -1 and -5, this would be -1. this would be minus 5. Which one is greater? Greater has to do with how much is closer to 1. Minus 1 is closer than minus 5. Minus 1 is greater. So minus 1 is greater than minus 5. Between minus 5 and minus 2. Minus 2 is here. Again, minus 2 is greater than minus 5. Between 0 and minus 3. 0 is greater than minus 3. So don't be confused by the value of the number. If it's minus, the greater the value means it's smaller. Minus 4 is smaller than minus 2. Minus 5 is smaller than minus 2. So don't let the value confuse you. The greater the negative number means it's smaller because it's farther away from the 0. Let's go back to our slide. Okay. Now, absolute value of an integer is, you have two little perpendicular lines, and then you put a or any number. It's just the distance from 0 to that number. It's never negative. For example, if I'm talking about what would be the absolute value of minus 1, minus 1, if I want to find this absolute value, I put it in those perpendicular thing, is equal to 1, just 1. If I want to find the absolute value of 5, is 5. Absolute value of minus 7 is 7. It's only the distance between that number and 0. And it can never be negative. All right? These are simple. As we are moving, in fact, toward the more algebra, things are become more simple. Algebra is very simple. If the integers have the same sign, you just add the absolute value. The sign of the sum is the same as the sign of the two. If the integers have different sign, you just have to subtract their absolute value, and the sign of the sum is the same as the sign of the number with the largest absolute value. We can do regrouping, we can do borrowing. For example, you have it in your PowerPoint. Minus 3 plus minus 2 is minus 5. Minus 3 plus 1, positive 1. What would be? What would you say? Is minus 2. So you just add the absolute value and use the sign of the number with the greatest absolute value. Here we have solve minus 8 plus minus 1 plus minus 8. Parenthesis minus 1 plus parenthesis minus 8. What's the answer? You have minus 1 plus minus 8. Answer is minus 9. If I had minus 1 plus positive 3, what would you say? You have two integers, different signs. One is minus 1, one is plus 3, and we are adding them together. Actually, you see, when it's minus, it takes away from 3, so the answer is 2, positive. Because if you go on the number line, here's the number line. If you go on the number line, if this is 0, and here is minus 1, here is plus 3, 1, 2, 3. You're adding these two. This is the distance for this one. This is the distance for this one. This is negative. This is positive. When you add them together, this is what you will left, only 2. So because this can be written also as -1 plus 3 can be written as +3 minus 1, which the answer is 2. Okay? So -1 plus -8, what was the answer? -9. You're moving away from 0. Rules for multiplication, which applies the same again for the division, is if you have the same signs, always positive. If you have mixed signs, it's always negative. Exponent indicate repeated multiplication. If you have 2 times 2 times 2, we write it 2 to the power of 3. Examples on page 244. I think this is clear. Okay, well, actually, let's do some of this. -8 parenthesis power of 2. We have -6. Then we have parenthesis power of 2. What would be the answer? This means -6 times -6. 6 times 6, 36. Negative times negative is plus. Okay? But if I change that just a little bit, if I make it like this, -6, if I put the power exponent here, then I get this is -6 minus 6 times 6, which is equal, 6 times 6, 36. The negative remains, so the answer is -36. See the difference? Just by moving the exponent from there, because when it's there, it applies both to number 6 and to the sign. But when I move it here, it only applies to 6. It does not apply to the negative number. All right? Okay. Same rules for division. If the signs are the same, positive. If the signs are different, negative. Order of operation, remember, you start with a parenthesis, then you do exponential, then you do multiplication and division in order from they occur from left to right, and then you finally do addition and subtraction in the order they appear from left to right. Parenthesis, exponent, multiply, divide, add, and subtract. Page 246 to 47. Let's look at what we have over there. For example, on page 246, we have one example, 6 to the power of 2 minus 24 divided by 2 to the power of 2 times 3 plus 1. So we start, you see, if you can see that the author makes it 6 to the power of 2 is 34. 2 to the power of 4 is 4 times 3. Then you have 36 minus 24 divided by 4. We do the division. Is 6. 6 times 3 plus 1. Actually, let me write it for you on the board. You see? Yeah. So we have 6 to the power of 2 minus 24. 24 divided by 2 times 3 plus 1. Okay? To make it simplified, you know, this is like if you put the parentheses around here, it makes it easier to understand. And if you put the parentheses over here, it makes it easier to understand. So 6 to the power of 2 is 36 minus, actually that 2 had a small, yeah, power of 2. Okay, so we have 24 divided by 2 to the power of 2 is 4. Then the whole thing times 3 plus 1. So 36, now I do inside the parentheses, 24 divided by 4 is 6 times 3 plus 1. So I have 36 minus 6 times 3, 18, plus 1. So 36, this makes it easier if you put the parentheses here, minus 19. So you end up with a number, oh, wait a minute, 36 plus 18 plus 1. Oh, I'm sorry, you have to go from, here's 1 or minus. $36 minus 18 is 18, plus 1 is 19. All right? So we go from left to right, left to right. There we go. Okay, 247. Okay, let's also look at the example number 8 on page 247. You have minus 6 to the power of 2 minus 5 minus 7 to the power of 2 times, when you have two parentheses, nothing between them, means time, minus 3. This 2 is over there. It applies to both the negative sign and the positive sign. So it becomes 36. 5 minus 7 is minus 2 to the power of 2 times minus 3. Again, 36 minus. This 2 applies to both the sign and the value of the number. This becomes plus 4 times minus 3. Now we do the multiplication first. Plus 4 times minus 3 is minus, the signs are different, 12. Okay? So we have 36 minus, now when you see this like a sign like this behind the parentheses, it means the multiplication. So you have minus times minus times plus 12, 36. Okay? Then it's equal. So notice we did the exponential. We started from inside the parentheses, then we did the exponent, then we did the multiplication, these two, and remember when you have minus behind the parentheses with no with no sign, it means positive. The minus sign, minus is positive. If, for example, this was plus, plus times negative will make it negative. Okay, so order of operation, please remember parentheses, exponent, multiplication and division, and addition and subtraction. And remember, you do the addition and subtraction from left to right. Rational numbers are set of numbers denoted by Q, set of all numbers of the form P divided by Q, where P and Q are integer and Q cannot be 0. Any number divided by 0 will give you infinity. Actually, you will have an error sign. Every rational number when it's expressed as a decimal number with either a terminating or a repeating decimal number. Fundamentals of law of rational numbers. When you have a fraction a over b and a number c which is not 0, a over b is equal to a times c, b over c. When you multiply the numerator, and the numerator is the top number. The number at the top is called numerator. The number at the bottom is called the denominator, and then you have that fraction sign. If you multiply both the top and the bottom of a fraction by the same number, the value doesn't change. 1 times 2 times 2 over 2 is the same as 2 over 4, which again can be simplified as 1 over 2. Now, converting a positive mixed number to an improper fraction. Improper fraction is a fraction that the numerator is greater than the numerator. You multiply the denominator of the fraction in the fixed number by the integer preceding it, then you add the product, obtain step 1 to the numerator. Let's look at some of the example that makes it easier. Or even on the PowerPoint, if you look, mixed number and improper fraction, you see you have 2 1/4. If I want to, that's a mixed number. If I want to change that to improper fraction, you take the 4 multiplied by 2, 8, you add it to the numerator. But let's look at examples on page 252. For example, we have this number, it's a mixed number, P 4/5. P 4 over 5. If I want to change, this is a mixed number. If I want to change it to an improper fraction, I take this denominator, multiply it by 3, 3 times 5, 15, 3 times 5, 15. And then I add this number to the numerator. That's 4 plus 15. We keep the same denominator. So the answer would be 19 over 5. Because if you divide that, you get this. All right? If you have, let's do another one. If you have -2, 3 over 4, again, take this, the denominator, multiply by the integer here, 4 times 2, 8, but remember, you have a negative sign. 4 times 2, 8, but that negative sign remains here, don't worry about it. 4 times 2, 8, you add it plus 3. So the answer is 11 over 4. Okay? Now, you can, if you have an improper fraction, you can convert that to a mixed number by division. Actually, we did this, for example, let's just look at this one. If I want to convert that, you're basically dividing 11 by 4. So 11 goes to 4 how many times? 2. So we get 3. So the answer here, look at the numbers. You have 2, 4, and 3. This becomes the denominator, this becomes the numerator, and this becomes the integer, right? So that's how we do. We take the quotient, this quotient becomes the integer, and the remainder becomes the numerator, and then you have the number here goes as a denominator. All right. Okay. And actually, that's what we are doing here. Converting positive improper fraction to a mixed number. As I said, you divide the quotient obtained in this step 1 is the integer part of the mixed number. The remainder is the numerator of the fraction. Denominator in the fraction of the mixed number will be the same as the denominator in the original fraction. I have it in the PowerPoint. 7/4. That's an improper fraction. Why? Because the numerator is greater than the denominator. We divide 7 by 4. 4 goes to 7 once. So you have the remainder of 3. The remainder becomes a numerator. The denominator remains the same. That your quotient becomes your whole point. A multiplication of fractions. When you have multiplication, just multiply the numerator and denominator by each other. Remember, this is only for multiplication. 2 over 5 times 3 to the power of 3 over 4. 2 times 3 is 6. 5 times 4, 20. And you can simplify that. 6 can be divided by 2, it becomes 3, 20 becomes 10. Division, when you want to do the division, is basically the same thing. The only thing you have to do, remember, when you're dividing the next fraction, the fraction that you want to divide by, you invert that and then change the sign to multiplication. 4 over 5 divided by 2 over 3 is the same as 4 over 5 times, then I invert the other fraction, 3 over 2. So it becomes 4 times 3, 12, 5 times 2, 10, and 12 over 10, you can change that to a mixed number because it's an improper fraction. 10 goes to 12 only one time, that becomes your integer. Then you have 12. Yeah. Then you have a remainder of 2, and when you simplify that, it becomes 1 over 5. You know, let me do that. We have 12 over 10. So we have 12 divided by 10 equals 1 time, 2, 10. So we have what we have. Remember, that becomes your integer. That becomes your numerator. That becomes the denominator remains the same. But this can be simplified. This becomes 1, and this becomes 5. 2 divided by 3 is 1, so it's 1 over 5. Okay. When we want to add fractions, when we come to addition or subtraction, we have to find the least common denominator. And to do that, you multiply top and the bottom of the denominator by the same number. You know, we have this, for example, 2 1 over 3rd plus 3 3/4. First of all, we add their whole number, 2 plus 3, 5. Then we have 1 over 3 plus 3 over 4. Let's do that again. Okay, 2 1/3 plus 3 3/4. Okay. First, we come and take their whole numbers and add them together. 2 plus 3, 5. This is your whole number here. There it comes. You don't know what those things. Then we add 1 over 3 plus 3 over 4. In order to do that, I need to make their denominators the same. What I do is I multiply 1/3 by this denominator plus, and I multiply 3/4 by this denominator. So you get 4 over 12 plus 9 over 12. And that is equal to, when the denominator is the same, you just add the 4 plus 3, 4 plus 9, which you get 13 over 12. Okay? Now, here is an improper fraction. When you want to add them together, we have to 9 over 12. Wait a minute. 13 over 12. Yeah, 1 over 13 over 12. And so if you divide that, 13 over 12 goes 1 time, get 1. So the answer for that is 12, 1 over 12. So you have 1 over 12, and 5. You add this 1 to this number, this becomes 6 over 1 over 12. As you can see, you add this one, this becomes 6. And 1 over 12. Because actually you have a whole number, 5 plus 1 over 12. Actually, what we have here is 5 plus 1 over 1 over 12. Add these two, we get 6 over 1 over 12. Okay? All right. We come to irrational number, and one of the mystery of this universe, which I believe God has put that in the universe, is the number pi, which never ends. Irrational number is a real number whose decimal representation is non-terminating, continues to infinity, non-repeating decimal numbers. Every non-negative real number A has a unique non-negative square root called principal square root, which is denoted by, that sign, the squares, we call that radical sign or the square sign. So basically, we are coming to the radical numbers. This is called the radical sign. And the number goes there, and whatever is here is a root. Second means the second square root. That's here. When we have two radical signs, if you want to multiply them, if the roots are the same, doesn't matter, any number, any real number, then you just write 1, AB, 1. Okay. If you have the division again, if you're dividing them, I have, I'm going to divide that by b, you can write it as here, which is the same, because the root is the same, and write it as one number AU. Okay. And A has to be greater than equal to 0, B has to be greater than 0. Same for division. Square roots. Let's look at adding and subtracting some of these square root. Let's look at example on page 266. For example, we want to find the square root of 75. 75 can be written as 25 times 3. 25 is 5 times 5 times 3. This is 5 to the power of 2 times 3. And when I don't write anything, it means it's 2. This divided by that brings this out, so it's 5 square root of 3. If we have, let's look at some of the multiplication. We have square root of 2 times the square root of 5, the same root, so it's 2 times 5 is equal to 10, and just stay there because it's a prime number. If we had a square root of 7 times square root of 7, this is equal to square root of 7 times 7, or square root of 7 to the power of 2. And this can be divided by that, and comes out 7. All right. Dividing the square roots, page 267. Again, some of the numbers, some of the examples. For example, if we have square root of 75 divided by square root of 3, since the same, we can write it as one number 75 divided by 3. Okay, 75, we mentioned, it can come out 75 over 3. Actually, 75 divided by 3 is 25, and 25 is 5 to the power of 2. This 2 gets divided by that 2, so the answer is 5. And same. Adding and subtracting square roots, let's go to page 268. If you have, we want to add 7 square root of 2 plus 5 square root of 2. What we do here, we factor I can factor out these two. I can bring it out. It becomes square root of 2, 7 plus 5. 7 plus 5, 12, square root of 2. Okay. Let's do the subtraction. If we have 2 square root of 5 minus 6 square root of 5. Okay. I have these two are the same. I factor them out. So I get square root of 5. Then I have 2 minus 6. 2 minus 6 has a larger value. So minus 4 the square root of 5. All right? That's basically those. Real number and their properties. If an operation is performed on any two elements of a set and the result is an element of the set, then we have a set is closed. We say it's closed under that operation. We have number of properties, which are very important. Commutative properties, associative properties, and distributive. A plus B is the same as B plus A. It can commute. A times B is the same as B times A for all the real number A and B. Associative. A plus B parentheses plus C is the same as A plus B plus C. You can add A and B first or B and C first when they have the same operation. Same with multiplication. And remember, it has to be the same operation in order to do that. Distributive is like this. If you have a number A time parentheses B plus C, the result is A times B, A times C. All right? We come to exponent and scientific notation. Expression 5 to power of 2 means 5 is raised to exponent 2. 5 is the base. The 2 is the exponent. 5 to power of number 2. Let's look at some properties, some on page 282. You know, when we have b to power of m on page 282, I'm looking at that table, table 5.4, time b to power of n, the bases are the same, the exponent are different. You keep the base, you add the exponent. 9 to power of 6 times 9 to power of 12 is same as 9 to power of 18. When you divide, or not divide, well, if you want to divide b to power of m divided by b to power of n, you keep the base, you subtract the exponent. When you have b to power of m times parentheses, again, to power of n, it's same as b to power of mn. Any number to power of 0 is equal to 1. If you have a number to power of negative is same as that number goes to the denominator of fraction, numerator is 1 with the power of, to the power of positive. For example, if I have 7 to power of minus 2, this is the same as 1 to power of 7 to power of 2. I just bring this into the denominator, change the sign, the numerator is 1. Okay? All right. We talked about this. All right. On the PowerPoint, if I have a to power of n times a to power of n is a to power of m plus n. If I have a to power of m divided by a to power of n is a to power of m minus n. If I have a to power of m parenthesis power of n, it's a to power of m n multiply. And a is not 0. Okay, scientific notation. Basically, the scientific notation is decimal notation and scientific notation. This is scientific notation. You have a number times 10 to power of n, for example. This is called scientific notation. A is a number greater than or equal to 1, less than 10, and n is an integer. If you want to change from scientific notation to decimal notation, let me give you an example. Let's go to page 285. For example, you have 2.6 times 10 to the power of 7. 2.6 times 10 to the power of 7. They have written this as a scientific notation. I want to change that to decimal representation. When this is positive, go here, here's a decimal point, okay? That's not a multiplication, this is decimal. Write it 26, then from 7, it goes 1 for the decimal, for this decimal number, 1, 2, 3, 4, 5, 6. That's same as this. 2,600,000. All right, let's look at another example. 1.1 times to 10 minus 4. No, that's good. We have a negative. 1.1 power of 10 minus 4. 1.1 times 10 to the power of minus 4. I want to write it as decimal. So, first write the 1.1 or 11 minus 4, move it this way, and you want it decimal point. So I move 1, 2, 3, 4, decimal 0. Okay. All right. If you want to convert decimals to scientific notation, if you want to do the other way around, let's look at page 286. And you can read the instructions on the PowerPoint or in our textbook. For example, 4,600,000. We want to do reverse. You have 4,600,000. We want to write in scientific notation. So I write 4 point decimal 6 times 10 to the power of, what should go there? Put 1 here. 1, 2, 3, 4, 5, 6. 4.6 times 10 to the power of 6. Okay, let's do one which is with a, which ends up giving us a negative exponent. Okay. If I have decimal number like this, how do I write it into a scientific form? So first, bring this here, 23. I put a decimal value here, but if I do that, 1, 2, 3, 4, 5. 10 to the power of negative or positive? Negative. Okay. 10 to the power of minus 5. All right. Computation with scientific notation, page 287, 288. Okay. The basic rule is right there. Let's write the basic rule. If we have A times 10 to the power of n multiply B times 10 to the power of m is the same as A plus B times 10 to the power of n plus m. That's the fundamental rules. So when we want to use some example, they have it, for example, 3.4 times 10 to the power of 9 times 2 times 10 to the power of minus 5. So what do we do? First, we add these two. 3.4 plus 2, 5.4 times 10 to the power of, you have 9 minus 5. 9 minus 5. So 5.4 times 10 to the power of. Okay. Oh, I'm sorry, I made a mistake here. The rule is should be times, not plus. Hello. Hi. Oh, sorry. I'm recording right now. Sorry about that. So you have A times B. I'm sorry, this I made a mistake. It should be 5, not 3.4 times 2, not added. Sorry. So you could be 6.8. All right. Or you can write it even in a regular format. It will be 68. Moving forward, 1, 2, 3, 4. Okay. So I'm sorry. So remember, if this is the rule for addition, if you have multiplication, if you have A times 10 to the power of n divided by B times 10 to the power of m, the rule is this: A divided by B times 10 to the power of n minus m. That's the rule, okay? All right. Arithmetic and geometric sequences, sequence in which terms after the first term differs from the preceding one by a constant amount is called arithmetic, and the difference is called the common difference. For example, if we go to page 294, example that you have at the top of the page 294, you have 29, 31, 33, 35, 37. If you notice, they are changing by 2. 21 to 31 is 2, 31 to 33, the difference is 2. So it's an arithmetic sequence. The common difference is 2. I think, if we have, for example, 5, 3, 1, minus 3, and minus 5. From 5 to 3, you go, from 5 to 3, you go down. So the difference is minus 2. From 3 to 1, you go down again 2. So the difference is minus 2, and it's an arithmetic sequence. From 1 to minus 1, the difference is again minus 2. All right. I think that's it, guys. I hope this is helpful. If you have any question, feel free to contact me. And I hope you were able to see everything, and I recorded it. Again, any question, remember to contact me again. So please remember, for PowerPoint presentation, submit all your PowerPoint presentation for our other book, the Nichols book. The deadline is session 7. I appreciate if everybody submit their presentation by that time. I wish you the best, pray for you, hope you all do good. In fact, let's have a prayer. Father God, I pray that you bless all these dear students, not only in this class, if the other classes that they are taking, may they be able to use what they learn for your service and your ministry, for your glory. For in Jesus' mighty name we pray. Amen. Okay, take care, guys. Bye-bye.